Okay, so, oh wow, nobody's here. Okay, so, two mathematicians are sitting in a bar, and they're complaining about how little people know about math. They're sort of upset about this, and so one of them goes to the bathroom, and the other mathematician decides to play a joke on his friend, and so he calls over the waitress and says, "Look, I'm going to ask you a question, and I want you to answer x cubed over 3." Okay, and the waitress sort of laughs at this and says, okay, x cubed over 3, x cubed over 3, x cubed, and she walks away. And then, so the other mathematician comes out, says, I don't think it's so bad. I think people know math better than you think. And the other mathematicians, what? Okay, well, let's try something. So he calls the waitress over and says, "What's the integral of x squared?" And she says, "X cubed over 3." And the other mathematician is like, "Oh my God." And then the waitress says, "Plus c." Okay, so okay, so we're going to do some reductions. We're going to go through the rest of the chapter, okay? Is there any questions, any concerns about anything? Okay. So last time Christos showed you this reduction from three-dimensional matching to, from 3-sat to three-dimensional matching. Okay, he showed you how to code up this reduction. Okay, so what we're going to do today is we're going to do a bunch of other problems. Okay, 0-1 equality is the first time. Okay, 0-1 equality is you're given an m by n matrix. Does there exist a 0-1 vector x equals x1 through xn where ax equals 1, and where this 1 on the right-hand side is the vector 1? Okay? So really, this is just a way to express a bunch of equations where you have variables x1 through xn, and they could take on values of 0 or 1, and you have a bunch of equations, and each one should add up to 1. Does that make sense? Okay, so this is just a matrix form, but it's just you have a set of equations and 0, 1 variables, and you want each equation to add up to 1. The equation is, the right-hand side happens to be 1. Okay? Yeah. Yeah, it's going to be kind of like a bunch of subset sum, sort of, yeah. I mean, it's a little different, but yeah, I mean, we'll see that it is very related to subset sum. He asked if it's related to subset sum, and it is. But let's just to get a little bit of intuition, if you have an equation, x1 plus x3 plus x4 equals 1, and all the variables are 0 or 1, how many of them can be 1? 1. Right? 2 can't be 1, and they can't all be 0. So really it's asking exactly one of them should be 1 in each equation. Okay, so that's just to get some intuition. We're going to work with this particular problem a few times, so it's valuable to get some intuition. Okay. Okay, so remember three-dimensional matching, you have m boys, girls, and pets. And you have a set of n compatible triplets. Okay, these are people, triplets that are all happy with each other. Okay, so you want to find a complete matching. You want to find a subset of triplets where every boy, girl, and pet is in one of the triplets, and in exactly one of the triplets, right? So you can't share pets, and you can't share boys, and all that stuff is not happening, okay, in this solution, right? Okay, so xi equals 1, so we're going to translate, okay, a reduction is in some sense a translation. We're given a particular instance of this three-dimensional matching, which is a set of triplets, right? That's what we start with, and we want to produce an instance of the 0-1 equality problem, okay? So I have this set of triplets, and what I'm trying to produce is a set of equations. Okay, so what the idea of my reduction is that xi equals 1 indicates that the triplet I is used in the matching. Okay, so I'm going to have a variable in some sense in my new equation, in my new system, for each triplet. And when that xi equals 1, that means I'm using that triplet. And when xi equals 0, it means I'm not using that triplet. Okay, for each boy or girl or pet, you're going to introduce an equation. And what that equation is going to say, the sum over the triplets t that contain the boy of xt, the sum of these variable values over these triplets, that should be your equation. Okay, that should equal 1, because that's going to be your matrix. Okay? Does this make sense? This is a pretty straightforward reduction. It says xi indicates whether you use a triplet or not, and now for every boy, girl, and pet, at least one of the triplets, exactly one of the triplets should be used. Right? So it's pretty... Okay, xt is... Okay, so say you have a three-dimensional matching, and you want to show there's a 0-1 equality solution. If you want to show there's a solution to the three-dimensional matching, original three-dimensional matching problem, if and only if, that's what the double arrow is, there's a 0-1 equality solution. And it should, this coding up should have made this almost obvious anyway. So if xt, we're going to set xt to be 1 if and only if for each triplet t in the matching. So if there's a t that's going to be actually in the matching, you set the xt equal to 1. Okay, now each boy, if it's a valid matching, each boy is in exactly one triplet. Each boy, girl, or pet is in exactly one triplet, which means that each corresponding equation is satisfied because you need exactly one of those xi's to be true in those equations. Okay? So that's the proof. This is a very simple reduction, right? It just says, okay. But it's always simple. The simplest reduction to make are ones where you have a very powerful thing you're reducing to. So 0-1 equality happens to be a very, very nice thing, right? You can represent decisions with these 0-1 variables. And it sort of translates almost immediately from three-dimensional matching. Okay? So now you were asking about subset sum. Now I'm going to show that subset sum is at least as hard as a 0-1 equality. Okay? So do people see how that might be possible? How might you code it up? So remember subset sum. What do you get? What's your input to subset sum? It's a set of numbers, a1 through an, and you want to see if a subset of that can be, and a number b, and you want to see if you could add up a subset of that to equal b. Okay? So it's kind of like a knapsack type problem. Okay? So I want to pick her. Okay, so let's look at this example. And remember, for 0-1 equality, we get a matrix. So 0-1 equality, you can sort of see it as finding a subset again. Okay, find a subset of columns that adds to the all ones. Okay? So subset sum is you're trying to find a subset of numbers that adds up to the number b. And here, 0-1 equality, you're finding a subset of columns that adds to the all ones, right? That's really what you're doing. When you take these variables and you set some of them to 1 and some of them to 0, you're multiplying a times x here, right? And a times x really says you're adding up the columns, right, according to the multipliers by x. So now since x is a 0-1 vector, it says you're just picking a subset of the columns to add up. Okay, so that's what the 0-1 equality does. So there's this very similar flavor here, right? So how do we use the subset sum problem to sort of find a solution to this problem? Okay? So what might we do? So it's a subset of columns. So one thing we could do is we could treat each column as a number, right? Because we should assign a number according to each column, right? Because we're trying to find a subset of numbers, a subset of columns. Let's treat each column as a number, okay? And then now we're saying let's add up these columns or numbers to get a number, or add up these columns to get a vector, which is all ones. Okay, so how might we do that? Well, we're going to treat the columns as a number, and this is how we code it up. So we'll let A1, which is the first column, be a number base n plus 1. Okay, here n is 4, n is 4, right? So n plus 1 is 5. Okay, I'm treating the first column as a number base 5, right? So A1 is equal to, in the first bit there, the highest order bit, it's 5 cubed, right? That's the way base works, right? Okay, so this is 1 times 5 cubed plus 0 times 5 squared plus, right, because this one is 0, and 1 times 5 plus 1. Okay, so that number, so I'm translating the 0, 1 equality into a subset sum problem. And 131 is a number that I'm going to represent column 1 for. Okay? So did people understand this? Any questions? Okay, so now my subset sum problem consists of these 4 numbers: 131, 31, 150, and 125. Okay, what else does subset sum need for its input? Yeah. Yeah, so he's suggesting this number B should be the number that corresponds to the representation of all ones, of the all ones vector in this base 5. Okay? So that is 125 plus 25 plus 5 plus 1, which is 156. Okay, so this is, you can ignore this calculation. Now you have just a subset sum problem. You have a set of 4 numbers, and you want to see if there's a subset that adds up to 156. Okay, does that make sense? Yeah. N is the number of columns. No, this just happens to be square. It totally doesn't have to be square. Yeah. So B is the number that is represented by n ones, which is base n plus 1. Okay. So now, does somebody see a solution to the subset sum problem? Uh-oh. 31 and 125 is a solution to the subset sum problem, right? 31 plus 125 is 156, so that's a subset of numbers that adds up to the 156. Okay, and now, does somebody see a subset? Does somebody see a solution to the 0, 1 equality? Yeah, the second column and the fourth column. Do people see the correspondence? Okay, so that's the mapping. Right? Yeah. Yeah. So why should it be base n plus 1? Does anybody understand why we use base n plus 1? Yeah. Right. Yeah. So there's a problem with numbers. If you used a base, say 2, you get some weird stuff happening, right? You know what happens when you 1, 1, 1, 1. What happens here? Base 2. You get a 1. You get a carry, right? So you don't want any carries to happen. Why don't you want any carries to happen? Because then you're not really what you want. Each row. So when you're adding up these columns in the 0, 1 equality constraint, You want each row to be more or less separate, right? You want this variable x1 plus x2, x2 plus x3. You don't want x2 plus x3 plus whatever happened in the row above you, right? So, yeah. You don't need to represent all numbers. Okay, so he had a good question. His question is, he says, I can't really represent all the possible inputs to subset sum. And he's correct. But we don't need to show that all the possible inputs are hard. We just need to show there's some subset of inputs that are hard. Okay, so this is a big deal in reductions. You don't need to show that every instance is hard, because we're going from 0, 1 equality. We need to be able to, what we need to do is be able to translate every one of these problems into a problem of that form. Okay? We don't need to translate to every, it doesn't need to be onto. Okay? The reductions need to be, you need to have a value, you need to have a way to translate every instance here into an instance there, but you don't have to hit every instance there. Okay? Yeah. Because it won't give you integers. What? Yeah, you could do it mod 2. It would work mod 2, but that's not what we're doing. Yeah. And what you're saying is the answer is, I don't know, I mean, I can't work out the counterexample or why that doesn't work exactly. I know it doesn't because 0, 1 equality reduces from 3-dimensional matching. We don't know how to solve it. We don't know how to solve this one. Okay, it's famously hard to solve. So Gaussian elimination by itself is definitely not going to work. And the short answer is it's going to give you integers. It's not going to give you integers. And now you took another step, and I don't completely understand this step. So we could talk about it. Okay. So this is I did it kind of slow because I really want you to understand a few moving parts here, right? We're translating over. We need to find this careful correspondence. We don't have to hit every instance over here for subset sum. That was a good question. And you have to sometimes be pretty clever about how you do the translation. You can't just treat it as a number, because you need to keep these rows separate. And this base n plus 1 makes sure that nothing happens in one column will affect the next column, right? Because these are all just ones. Okay? So you'll never get a carry. Okay, so the Zoe solution is a subset. There is a Zoe solution that's a subset of columns, if and only if there's a solution to the new problem. Okay, so, wait a second. Now this is a problem, right? Because we all gave dynamic programs for subset sum. Right, we know an efficient solution for the subset sum problem. Do people remember that? Who remembers that there's an efficient solution? What? Well, it's sort of efficient, right? I mean, it's we taught it to you. We want you to use it, so... Yeah, so let's go over this. Let's go over this. We think it's a useful algorithm, this dynamic programming algorithm. We do. We actually do think it's a useful algorithm. But let's just see where the different assumptions lie, okay? So here's the dynamic program. You have a table, BIK is true if a subset of A1 through AI adds to K. Okay, this is one. There's probably a number of ways to do this. Okay, so the recurrence is B, with no items, you don't add up. K is false. B00 should be true. Okay? Now, BIK is basically true if with the first I minus 1 items, you can get a subset of them that add up to K minus AI. Right? Because if you have a subset of them that add up to k minus ai, then you could add in ai, and then you have a new solution. Okay? Okay, so this is the dynamic program. It's pretty fast. It's pretty fast, right? It seems pretty fast. So first of all, I said it's as hard as 3SAT or Zoe or three-dimensional matching, but it's easy because of the dynamic programming. So let's look at why the details of what we mean by hard and easy here. Okay? So it's easy in the sense that we can bound this running time. It's O of k times n. Okay? So in our reduction, we did something really wacky. We used really big numbers. These are non-intuitive for us because we really wouldn't use numbers this big. It's not even reasonable. So this is why this is both the reasonable answer and why you need to be a little careful. Okay? Because these numbers, what is k? K is for example, this number b, which is this number b, which is n plus 1 to the m. So now if you plug in this dynamic programming solution in for using, say, subset sum to solve 0-1 equality, you get a running time bound of this, which is exponential, right? It's very large. Okay? Yeah. M is the number of rows. Okay, so this is the tension here. So subset sum is NP hard in a sense, but only with really very large numbers. And you need those very large numbers to actually simulate 0-1 equality. So if the numbers happen to be reasonable, then it's a perfectly fine algorithm to do. Okay, but you have to be careful. You have to be careful what you mean here. Okay. Okay, so now. Integer linear programming. This is really easy. This is one of these things that you guys should already be caught up with because you did this problem 310 with the A through F, right? This is a generalization. Integer linear programming, 0-1 equality tells you here's a set of equations where all the solutions need to be integral. And is there an integral solution? Okay, so integer linear programming is more general than that. It says, is there an integer solution to this problem? Given ax less than or equal to b, is there an integer solution? That's one version of integer linear programming. So Zoe's it's a special case. So the difference is 0-1 equality has an equality and this has an inequality, but we already know how to deal with that, right? You can write an equality as two inequalities in this way. Both x1 plus x2 is less than or equal to 4, and x1 plus x2 is greater than or equal to 4. Now, x1 plus x2 is greater than or equal to 4, you just take negatives and then you get a less than again. And you get the form you want in the linear program where you have less thans. Okay? Okay, so now you also want to add a variable that says, maybe there should be a 1 here. Yeah, this should be a 1. Sorry. This should be a 1. It says that the variables are not larger than 1. Okay, so you can express 0-1 equality as an integer linear program. Therefore, integer linear programs are harder. That's a reduction. Okay? So, okay. So now, okay. So now let's go over this a series reduction. All these are pretty straightforward. Okay, so this one's a little bit more. It has a little more to it. Okay, so given a graph, you want to find a cycle that visits every vertex exactly once. That's the Rudrata cycle problem. Okay. Okay, so this is a little more interesting. Those were all number problems. I personally like graphs. So here's a graph. Does it have a Rudrata cycle? So, okay, well, okay, let me try to find one. Okay, can I go from D? So I go from A to B, B to C. Now I can go from D to B. So that's not good, right? Because I'm repeating a node. Okay, so who still thinks the answer is yes? Okay, let's try again. Uh-oh. Okay, so, well, okay, so that's a Rudrata cycle. Does that make sense? I can go from A to B, B to D, and C to D, A to B, B to D, D to C, and C to A. I visited each node exactly once. Okay, so this other one was bad because I can't go from D to anywhere without visiting it again. Okay, so the idea is you have to find a cycle that visits every vertex exactly once. Yeah.
Wait, you have to go in order, so I can go A, B, D, C.
Yeah, that's what I did.
No, A, B, D, C.
Yeah, that's this one. Yeah, so there is a solution to this one. A to B, B to D, D to C, and C to A. So yeah, I do that too. I sometimes try to think of a solution instead of listening, but then that's good. So, okay. Is that clear what a Rudrata cycle is and what it isn't? And is it also clear that it's not completely trivial to see how to do this? Right? I wanted to show you like a little puzzle here because actually it's not kind of a accident that these things are hard. They really are hard. Even if you put in small examples, often you're like, oh, I don't really know. You don't have a good idea of how to proceed. Okay, so that's the problem. Like with MST, we could write some structure, we wrote a theorem, and we could use the theorem to then prove our algorithm. NP hard problems, generally we don't have theorems for. We don't know how to proceed next. We don't have any insight. Here it's a small example, so I know what the answer is. But in general, these things can be really hard. I mean, there's no particular reason why this one worked and the previous one didn't, other than it just does, right? So, or at least we don't have good reasons for these things. There really isn't a structure here. So, okay. So the lesson here actually for algorithms is you need to prove a theorem in some sense, almost always, if you want to find an efficient algorithm. And NP hard problems in general, you can't prove good theorems for. Okay. I mean, we will get to something when we do deal with coping with NP completeness. We'll prove theorems that give us some insight into the solutions for these problems, but not all the way. Okay, so so you're given an instance. So instead of doing Rudrata cycle, we're going to do Rudrata cycle. We're going to do it in steps. Instead of reducing from 0-1 equality to Rudrata cycle, we're going to reduce to this other problem. Okay, so this other problem is one where you're given a graph and a set of pairs of edges. Okay, so the output is a cycle. Again, it's a Rudrata cycle. You visit every node exactly once. That should say exactly once. And for each pair, so each pair in C, now you have this set of pairs of edges. You use exactly one of these edges. Okay, so let's look at an example here. So now parallel edges are possible. It makes sense to have parallel edges. Okay, so here I have the same graph I had before, except I have 3 parallel edges between C and A. Okay, and now I'm going to say there's an edge pair, CA, this blue edge here, and BD. Okay, so now there's this edge here and this edge here, and they're in a pair. So any Rudrata cycle must use both of these. Is that right? Any Rudrata cycle must use both of these, right? No? Yes? Who thinks they should use both of these? Okay, so let's go back and read the definition. Okay, so the output cycle, it's a little hard to parse, so that's why I want to do this. Otherwise, the rest of it makes no sense. Okay, so output a cycle that visits every node, and for each pair, so this is one of our pairs in C, you use exactly one of these. So you have to use either this or this, and you have to use one of them. Okay? So is there a solution that does that? Well, yeah. That's the solution, right? It uses B to D. We see that this solution uses B to D, and it does not use A to C. the blue A to C. It uses a different A to C. Does that make sense? Okay, so I just this example is just trying to get you to parse the definition pretty carefully, because we're going to need that parsing to do the reduction. Yeah.
How do you make it, like, can you make an adjacency matrix for that?
Yeah, you just make an adjacency matrix with one. You just have the edge have a name, right? That's all you need, right? I mean, what's in a name? Everything. Everything is in it. Does that make sense? I mean, we're just saying this name, the name of this edge, is the blue C to A. Okay? It has a name, and the name is the blue edge from C to A. Okay? And this other one is the black edge from C to A, and the other one is, well, the other black edge from C to A. Okay, but each one of the edges should have a name, right? That's true. You could always have parallel arcs. You just have to name them, and you use an adjacency list, right? You can use an adjacency list where your node is adjacent to this object, which is called an edge. No. You don't want to use a matrix. You're right. It's an adjacency list. You want to? I mean, you wouldn't normally call it an adjacency matrix. I mean, I guess you can make some representation that looks like a matrix, and that's fine. Yeah, sorry, I misunderstood. But yeah.
Why does it matter that you name them? Why don't you just, as long as there exists an edge from C to A that the user can draw a cycle, just check.
Okay, so yeah, he asked why am I doing this? Any of these three edges ought to be good enough, right? Okay, so I'm just making up this problem, but I don't know whether this problem is well motivated or not. Maybe I can make up something like, some of these pairs of edges, there's an ice cream stand on each of them. You need to have your ice cream, blah. Okay, so you can say that, but you can't have two ice creams because two ice creams is bad for you, But it's a bit of a made-up condition, and it's a little subtle, and that's why I'm going so slow, because I really want you to understand this condition, and then I'm going to fix the condition. I'm going to take away the condition. I'm going to show we don't actually need the condition later. Yeah, the condition being E prime, that I have pairs of edges, and those pairs of edges, the reason I'm going to add that condition is it's going to be very useful for me to simulate 0-1 equality. Okay, what is life? Okay, life is about simulating Boolean logic. Okay? That's what we're doing here, right? That's what these NP completeness reductions are. We're saying we can simulate SAT. What is SAT? Boolean logic. What is Boolean logic? It's a computer. We're computer scientists. Everything is a computer, right? It's not just everything, not just a computer scientist. This is really the world. Everything in the world is a computer, right? That's really what it is. Except for the fact there's some glitches there, but that's what it is. And so we're showing you that this particular object is as powerful as the world. And so we have to do that. It takes a bit of doing, right? We're grabbing the world and we're building a computer out of it. So we're saying this particular object, we can actually build a very general purpose thing. Okay, so and this condition is going to allow us to simulate Boolean variables, and you'll see that in a moment. Yeah. Yeah. Yeah, then there would be no solution. Yeah. Yeah, he's asking, what if I added some pairs here and then I couldn't actually find a solution that did it? Well, then there would be no solution. Yeah. I want to find a solution if there is one. If there isn't, I want to say no. Yeah.
So what's the point of parallel edges?
Again, it's just we're going to use them in our reduction. And you'll see in a moment how we do it. So hopefully you're dying to see how we use them in the reduction. Okay, so, yeah.
What is C subset of E by E pairs of edges?
It's just a notation for saying pairs of edges, a set of pairs of edges. Yeah, E is a set of edges. E cross E means just a tuple with one edge and another edge. Okay, it's just notation. So But if you don't understand the notation, it's just pairs of edges, a set of pairs of edges. Okay? So, how do we reduce to Rudrata cycle with edge pair constraints? Okay, so how will we do that? Okay, so what do we need to simulate in 0-1 equality? Let's remember 0-1 equality. We need to simulate the variables and we need to simulate the equations, right? You saw that in three-dimensional matching, right? So he said, oh, you have sat, and I'm going to tell you how to simulate each. I'm going to build you something that simulates each variable and something that sort of represents each clause. So we're going to do something analogous. We're going to find something for each equation. What we're going to do is we're going to make a pair of nodes. We need to translate the set of equations and variables into a graph. Okay? So for each equation, we're going to make a pair of nodes and an edge for each non-zero variable. Okay? So it looks like this. So we have, in our new graph, we're going to have, for this equation, here's this equation, x1 plus x3 plus x4 equals 1. I'm going to write down a pair of nodes. Okay, so there's two pairs of nodes. And then I'm going to put 3 edges between them. Okay? And then I'm going to have an edge for x1, and an edge for x3, and an edge for x4. So it's pretty natural. I mean, but now I'm using parallel edges here, very much so. Okay? So now, for each xi, I'm going to have a pair of nodes with what should I always have when I simulate a variable? Well, I should have something that corresponds to true and something that corresponds to false for Boolean variables. For 0-1 variables, I should have something that corresponds to 0 and something that corresponds to 1. Okay? So I'm going to do the same thing. I'm going to have a pair of edges, one of which sort of corresponds to xi equals 0, and another one that corresponds to xi equals 1. Okay, so for every variable, I introduce this kind of gadget, and then I introduce that kind of gadget. And now I need to connect them up into a graph. Okay? Okay, first of all, I'm also going to add a pair. Okay, so remember this Rudrata cycle has edge pairs. Okay, paired edges. Okay? So now I'm going to add a pair. And the pair in this particular representation is, for this equation and this variable, is x1 and the red edge there. The two red edges. Okay? So it says either, in my Rudrata cycle, either I should use this edge or I should use that edge. Okay? And I have to use exactly one of them. Okay? Whatever Rudrata cycle says. Now this, yeah. More or less. He asked, does that red edge up in the equation gadget, does that correspond to x1 equal 1? And yes. Okay? So another thing to notice is that in this equation, x1 plus x3 plus x4 equals 1, how many of those xi's is equal to 1? If it's satisfied. Exactly 1. So now you can see where this edge, which edge choice you should make. If you have a satisfying assignment for 0-1 equality, you can see how to translate that into at least a set of selections here that respect the edge pairs. Right? Because for any variable you just set, in each one of these guys, let's say we have to choose an edge from each one of these gadgets. One edge. So if I have a 0-1 equality assignment, and that assignment assigns 1 to x1, then I use this edge. Okay? And if I use this edge, that tells me that equation gadget can use the x1 edge. Okay? On the other hand, if I use this edge, that equation gadget cannot use the x1 edge. Right? I've already used it up. Okay? So that's just getting some intuition. Yeah.
Okay, so I just want to get my head around this. So in your Rudrata, in the graph, you're gonna, if you just have like one edge between two pairs of nodes, then you're gonna create another edge, which is gonna say, okay, I'm either gonna use this edge or I'm not gonna use this edge.
I don't have a graph yet. I'm creating the whole graph from scratch. And this is how I'm starting. I haven't finished the graph, but this is how I'm starting. First, yeah.
0 means I'm not using this edge, and 1 means I am using this edge.
No. There's two edges here, and this edge corresponds to x1 equals 0, and it doesn't mean you're not or using the edge. I mean, it says what we're going to do is we're going to have a 0-1 equality assignment. And that's going to assign something to 0 or 1, right? This variable, x1 to 0 or 1. If that 0-1 equality assignment assigns this variable to 0, it says I'm going to use this edge. Let me give you another. I won't. Yeah. Let me rush by it so you don't understand. So this pair corresponds to the color. Yeah, exactly. I illustrated one pair that's going to be in our whole big thing. Yeah. Yeah, so then the gadgets for x3 and x4, they would all pick the other pair. Yeah. If x1 was 1, then you could pick that one. But you know in a valid assignment, what would x3 and x4 be? 0. So therefore, those gadgets would be set to 0. Yeah.
So then doesn't that also correspond to my intuition of it, which was that if you're going to pick an edge over here, the one that actually pick is going to be 1 and all other ones will be 0.
Yeah. Yeah.
Is this somewhat similar to like a max flow problem?
He asks if it's similar to a max flow problem. Yeah, just like 3D matching is similar. In some sense, it's similar, but it's just different enough where it becomes impossible. So and that's like matching is easy, and 3-dimensional matching you fail on, right? Okay, yeah. So, so now now I only told you a part of it. I just told you how to build all the pieces. Now, how do we connect all these pieces? In the most trivial way possible. We put them in a simple cycle. Okay. So just to give you a picture, I'll give you a picture. Okay. So this is the 0-1 equality problem up here. Okay. So the first row says you have an equation x1 plus x3 plus x4. Which is this equation. And this is the equation gadget. You have 3 parallel edges. Okay, 1 for x1, 1 for x3, and 1 for x4. Right? The second row is x2 plus x3. This is the equation gadget. x1 plus x2, that's the third row. And x2 plus x3 is the fourth row. Okay? Now the equation gadgets are, you have 4 equations. So x1, x2, x3, and x4. The top edge corresponds to x1, corresponds to x1 being 0. The bottom edge corresponds to x1 being 1. Okay? So this is the gadget. So what do our edge pairs look like? Our edge pairs look like the following. This top edge corresponds to x1. This top edge corresponds to x1 being 0. So we put these two in a pair. It says in any Rudrata cycle that we're allowing here, that we have to choose exactly one of these. We have to choose either this one or this one, and exactly one of them. Okay? So that's the setup of this problem. That's this translation into this translation of 0-1 equality into the Rudrata cycle here. Okay, so do we know a solution here? What's the solution for the 0-1 equality problem? Okay, so it's x2 equals 1, and x4 equals 1. Okay, and x1 and x3 are 0. Okay, so the way we're going to translate that into the path, say the path, so the Rudrata cycle clearly has to go around the cycle, right? That's it. And so then the choice of the Rudrata cycle is just which edge through each one of these gadgets you use in each place. Okay? So now what we're going to say, if we know our satisfying assignment because it's a small problem and we know the answer. X2 equals 1 and x4 equals 1, x1 equals 0, so the Rudrata path will go up here, right? x2 will be 1, so it'll go down. x3 will be 0, so it goes up. and down, right? And now, what's the path through each one of these? Well, this one says, okay, so there's a path. We know how to set our variable edges. So how do we set our equation edges? Okay, so for x1, x3, which one is true here? x4. So we'll use the x4 edge, right? And why can we use x4 edge? Because we know this edge and this edge are in a pair. x4 and x4 are in a pair. Okay? But we know we're not using this edge because x4 is equal to 1. So we're using this edge. So therefore, we're allowed to select this edge. And in fact, we have to select this edge. And now for these other two edges, how do we know that the other pair, the edge corresponding to the other edge here is actually used? Well, we know in the real solution that these two are both 0. And if these two are both 0, we know that we're using the 0 edges here. So we are using the other end of the pair. Okay? So here's a solution. So here's a solution. It says x1 is 0. This equation is satisfied by the fourth variable. This equation is satisfied by the second variable. This equation is satisfied by the second variable. This equation is satisfied by the second variable. Yeah. Well, because it's not in, okay, so he asked if adding the edge constraint could make it so easy it's out of NP. What we're doing is we're adding the edge constraint and then using the problem with the edge constraint and showing that 0-1 equality can be reduced to it. So this problem here I'm showing is harder than 0-1 equality. Adding these constraints, I can use these constraints in a manner where I can simulate 0-1 equality. Okay, so I know it's hard. I mean, I could add it. It's not saying anytime I add any conditions, it doesn't make the problem easier. It does. I can tell you the answer. I can give you a problem where the answer is always no. Okay, that's an easy problem. I just add enough conditions where you can't, you have to be bigger than 6 foot, and you have to be coordinated, and you have to be Indian. And, these things may not happen very often, right? So no offense to other people but it is saying with these constraints, I've produced a problem that does simulate any problem in 0-1 equality. Okay? Okay, so let's just, so now you should have some intuition, and let's just polish off the proof, and here we're set, right? What we need to say is there's a solution for the 0-1 equality if and only if there's a solution to the Rudratra cycle. And basically, these things are so closely linked, you could just read the solution for one off the other. Yeah. With paired edges. Right. To this problem, yeah. Yeah. We'll do that in a few minutes. Okay, he says we need to finish with the Rudratra cycle, but we're not finished with the Rudratra cycle with edge pairs. Okay, so there is a solution for the 0-1 equality instance if and only if there's a Rudratra cycle in that instance that we produced. Okay, so now assignment to variables gives a path for the variable equations. That's easy, right? Because that's what they do. Okay, now you use the appropriate edge in the variable gadget. So if you have a solution to the 0-1 equality for any equation, there's exactly one edge, which is 1. So you use that edge in the gadget, in the equation gadget. Okay. So each edge pair either uses xi edge in the equation, or it uses the xi equals 0 edge in the variable gadget. It uses one of those. Okay? Since it uses one of those, that means each edge pair constraint is satisfied. So one edge in the edge pair is used. Okay? And the fact that a cycle is trivial because we just connected everything else in a cycle. Okay, now if a cycle, there's an assignment. Again, you just read the assignment off of the variable gadgets. Each variable gadget, either the edge, you use the top edge or the bottom edge. And whichever edge you use, you set the variable to be 0 or 1, depending on whether you use the top edge or the bottom edge. Yeah. Okay. Okay. Actually, we're going to have a break. So why don't you ask me in the break? Is that all right? Or unless, yeah. And then I'm just going to finish the slide and we'll have a break and then we can go back. Okay. So now make assignment according to which edge is in the variable. So now the edge pair constraint. Here you're starting with the cycle. And you're using, this is very important. You need to show how to connect the variable assignment to the equations. And here the edge pair constraints are doing that for you. They're saying if that variable is set to 0 there, I can't use that edge, that xi in my path across for this equation. Okay? So that's what it's saying. It says the value of that variable is influencing what I can do with this equation. That's what the edge pair constraint is doing. Okay? So the edge pair constraint basically says the edge used in the equation can't use the edge for x1 I equals 0. So that says the edge used for this equation must be set to 1 by this assignment. Since that variable is set to 1, then we know this equation is satisfied. Okay? Okay. So it's a valid 0, 1 equality assignment. Okay? Okay, so yeah, I'm going to give you a break, and then if you have questions about this, we can go over it during the break. Okay, so what were you asking? Uh-huh.
X1 is equal to 1. What's going to be used over here?
No, x1 is equal to 0. The top edge is 0.
Well, if it's equal to 1, like what does that correspond to here? Like just...
Yeah, it just says if x1 is equal to 1, it says that this guy better use this edge. Because the point is either this edge or this edge has to be used. So if you set x1 is equal to, because that's what the edge pair constraint says. Because we put these two edges in a pair. Yeah, we put these two in a pair. So the edge pair constraint says we have to use either this one or this one. Now if we set x1 to 1, that says we're using this edge, so we're not using this edge. So therefore we have to use this edge. Okay?
Okay. So the way that these, so this is the, we call them the variable gadgets, and this is the equation.
Mm-hmm.
So if you say 0 here, that means that you can't use this edge. If you say 1 here, that means that you must use this edge. Okay, so that's how they're related. That's like what I was asking earlier.
Yeah.
The condition between those.
Yeah.
Like, I thought 0 means you use it, 1 means you don't. But that's not from this. That just corresponds to the...
No, 0 and 1 just depends on, it tells you which one of the edges you use, yeah.
So then this and this, how does that relate to this?
Right, so this one has an edge pair with this and this.
Okay.
Okay.
So because that one is 0, that means we're not going to use
That one.
this. That means you're going to use this.
All right. All right.
Does that mean,
So there you go.
since that one is 1, that means we could use that, but since you're already using this, that's also a
No. You can't use this one because that one's being used.
How come this one gains a
But this one and this one are in pairs. Okay? So it says this one's not being used, so this one has to be used.
Okay, so because so we know x1 is going to be 0 and x2 we know is going to be 1.
Mm-hmm.
So because of both of these, like out here you saw
The fact, no, each one, you just go in order. You just say, well, this one, can I use this one? No, because I'm in an edge pair with this. So I can't use it. Okay, how about this one? Can I use this one? Oh, I can use it. And I better use it. I have to use it. Because this guy's not using it. Right, this is in an edge pair. So since these are in an edge pair, I have to use one of them. I'm not using this one, I better use this one. Okay? Now you would be in trouble if it says, I have to use this one and this one. But you know for 0, 1 equality, these things add up to 1. Only one of these is 1. So it says only one of these will I have to use. Right? It can't be that this can be 1. Okay, because what is this one? This must correspond to x3. And x3 is 0, so I can't use this one.
x3 is 0.
And yeah, so this one is in an edge pair with x3 equals 0.
So if it's 0 here, that means it's not going to be used there.
Yeah.
So 0 here means you're not going to use.
Exactly.
0 here means you're not going to use x1 there.
Or here, it's x1 is in a lot of pairs.
X1 corresponds to this one.
Yeah. Right. Right. So here's, I coded them from top to bottom, right? x1, x3, x4, yeah.
So x2 here, this is 1 x2, that means you should use it. That's what I'm using here.
Yeah. Sorry.
Okay, I got it.
I think you said a while ago that there might be like an extra credit bonus if you computer now.
Oh, did I say that, or did Christos say that? I think, yeah, I think we're probably not going to make an extra credit. We're just going to make it worth the homework. Yeah. So.
Gaussian elimination, isn't there a counterexample for Gaussian elimination when n is bigger than m? So then you have to figure out linear combination.
Right. N is bigger than m. You could always add extra variables. You could always add extra equations that are trivial.
But when you have like linearly columns, you set
Yeah, but yeah, that's one counter. That's one way to get it. But I think you can. I think it's mostly just because it's not integer.
Oh, that's what I'm saying.
Yeah.
Why it's not integer.
No, it's not integer anyway. Even for an n by n matrix with.
Because if you have multiple possible solutions, you have to scan forever to figure out which one only zeros and ones.
Well, that's not a proof. Yeah, but I mean, there might be some clever way to do it.
No,
But
I'm saying Gaussian elimination doesn't.
no, it doesn't. The Gaussian elimination gives you things that aren't integers, so it doesn't work right away. So even for an n by n matrix, it gives you things that aren't, right? You know, if you have a equation that looks like it's probably,
You can either say it works or it doesn't.
yeah, and it probably doesn't. There's lots of examples of where it doesn't. Yeah.
I think my question is kind of similar to Alex's question, but I got a little bit confused because I thought that when you, so I understand you make all the gadgets and then you just run the cycle and find the cycle.
No, you don't find one. You just say, if there is one, then there's also a solution for ZOE.
But I mean, isn't the whole, like, let's say you actually are solving by reduction, as in, like, you're reducing it, solving the Rajada cycle, and then transforming your answer back into...
Right. But that's not how, I mean, it's just, technically that's not how you should view it. You should view it as, if there's a solution here, there's a solution here.
If we're proving empty, like if
Right.
we're doing it to prove empty completeness, but if we're doing it like
Yeah.
to, like a reduction in general can be used to
But
make
there, yeah,
easier.
that's fine, yeah.
So my question is, like, I thought that, okay, once we've formed all these gadgets and we, I guess, run the process, like, or like
Get a solution, yeah, you get a solution.
so I was a little confused because it seemed like you were saying that for, you know how one of the edges represents I equals 0 and one equals represents xi equals 1?
Mm-hmm.
Then are we saying that you cannot use the
You have to be very localized in your argument. You have to say, for this equation, what happens?
Okay.
For this equation, you can only use the edge where xi is set to 1.
But I mean, is it set? I guess that's where I'm confused because I would think that like running the Rudrada cycle would
Right.
determine what we're setting.
Yeah, so what we're going to do is we're going to look at this and we're going to see what the setting is. Okay? So now we can't use this one if the variable is set to 0.
Right, but I guess that's my question. Where are we looking to see if it's at 0?
Yeah, right here. We look at it. No, we look at it. We look at the gadget.
But my question is it set to 0 there because it was set to 0?
No, we're setting to 0 as follows, right? If it uses the upper edge, we set it to 0.
Okay, so
Yeah.
it is what I thought.
Yeah. We set it to 0 if, yeah.
It's like the Rudrada cycle operates almost like naively. It can choose any such path that is satisfied.
Right. And then you look at it, you can derive an assignment. Okay. Okay. Okay, so, all right. So you guys want a joke or you guys want to get on with it? Okay. So, okay, so there's a mathematician, you probably have all heard this one. The mathematician was talking to a philosopher saying how great his life was, and, or her life, and said, well, let's say her life was. And says, all I need is a pencil and a paper and a waste paper basket. And, I'm good. I could do my work, and it's wonderful. And the philosopher says, oh, I could do you one better. I just need the pencil and paper. Pencil and infinite supplies of paper. Okay. I don't need the waste paper basket. Okay, sorry. Okay, never mind. Come on, you get it? You get it? Yeah. Have you seen a philosophy book? They're pretty long, and they don't really. Have you taken? Who's read Being in Time? Anybody read Being in Time? Okay, well, I read the words, but I don't understand a thing. So maybe that's how you feel when you go to my lecture. Okay, so I'm trying. Okay, so assignment. Okay, so we already did this. Okay, good. Okay, so it's valid. So now we want to get rid of this edge pair requirements, right? Rudrata cycle would look different. It didn't have this bizarre constraint. It's like cheating. We massively cheated. We said that Rudrata cycle was hard, and then we changed the problem to something completely different and said, okay, this is hard. And we called it Rudrata cycle, okay? That's about what it looks like, right? And so the question is, we have these weird edge pairs, right, where we have this condition that, you have to use either CD, that's an edge pair, CD and AB, and what the edge pair says, you can either connect CD or AB. You have to use one of them, okay? So that's what an edge pair is. So now we're going to just focus on this particular gadget. Can we enforce this condition using just regular Rudrata cycle? Okay, so that's what we need to show to polish off this proof. Okay, gadget. Okay, so so this is the gadget. So nice, right? Wow. Okay, this is not even a particularly complicated one. I think maybe Christos came up with this one, but he has gadgets where there's 5 pages of diagrams like this. Okay, so it can be very involved, this game. But now this gadget, I claim, either has to connect C or D, or B or A or B. It won't. You can't have a path from A to D here, which will work. You'll miss some node. So there is a path. This is a path that connects A to B, right? And it has to hit every node in the middle. And Rudrata cycle, right? You have to hit every node in the middle exactly once. So with this particular way of doing it, with this sort of parity, it's doing a bit of a parity thing. You can get through this gadget, you hit every node, and you go from A to B. Okay? There's also a way to do it from C to D. You go down, up, up. Okay? So there's no way to get through this gadget and hit every node exactly once and go from C to B or from A to D. Okay? Yeah.
Those nodes represent vertices, right?
They represent vertices, yeah. So the reason the vertices are important is because Rudrata cycle requires you to touch every vertex exactly once. And by using that condition, this is a gadget, and go ahead and try. You'll never be able to get through this gadget from C to B and hit every node in the middle. Okay? Now, who's going to pick up A and D? Those will be other edges that pick up A and D in the bigger construction. Okay? So what we did is this crazy, so you think, oh, come on, this is ridiculous. It's just cycle. We're trying to find a cycle. Well, the cycle is freaking obvious here, right? It's this one, right? But the hard part about Rudrata cycle is finding the cycle. So somehow, what these gadgets are doing, it's taking this thing and putting it together with this thing. So now instead of this nice graph you have where it's all a simple cycle, it's like, it's a big mess. Okay? So now you're going to get, I didn't do it, but, that would take me like the rest of the year to actually build the thing. But now you have a cycle, and then it's going to be hard to sort out where it goes. Okay? So the cycle part is hard, because you can do this very, very clever thing to sort of, in stages, build up, this gadget is now connecting these things that are really far apart in that cycle. Okay? Yeah. Yeah, so what you would do here, where am I going backwards? Which way am I? I'm going forward, okay. Okay, so for an edge pair here, you'd have this be C to D, and that be A to B. Okay, and so this red edge, all that middle part of that gadget we built would be these two edges together. Okay? And now for this edge actually is in more than one pair. So you'd have a gadget for each pair. Okay? So you have this edge is in this pair, it's also in this pair. So you'd have a gadget for this pair of edges, and a gadget for this pair of edges, and a gadget for this pair of edges, and so on. Okay, so it gets messy, which it should, right? Because it should get messy, because what we're trying to do is we're trying to show it's hard. It's simulating everything. So it should, that life should not be so easy to do everything, right? So, but still, okay, so we have this edge pair. Okay, so this is the gadget, and, with a little bit of work, you can show that you can't do anything else. Okay, so now I'm going to show that Rudrata cycle reduces to TSP, and this is an easy reduction, okay? So the TSP instance, so the Rudrata cycles, you're given a graph, you want to visit every node exactly once. The TSP instance, remember you want to have a distance between every pair of nodes, and you want to minimize the cost of a tour that visits everybody. Okay? So we're going to set d of ij to 1 if ij is an edge, and d of ij to 1 plus alpha if ij is not an edge. That should be not an edge. Okay? Okay, so Rudrata cycle, if there is a cycle that visits every node exactly once, there should be a TSP tour of cost n, right? Use n edges. If not, then you're going to have to visit a node more than once to visit every city. Okay? So, or you'll have to use one of these non-edges. okay, to visit every city. So the cost of the TSP tour, if it's less than or equal to n, if you do find a tour of less than or equal to n, that means you've only used the edges in the original graph, and you visited everybody. So that means there's a Rodata cycle. So either way, if there's a Rodata cycle, there's a TSP of cost n. If there's a TSP of cost less than or equal to n, then there's a Rodata cycle. Yeah. What? Yeah, it could be equals n. It should be equals n. It could be equals n. Okay. The reason I said less than or equal to, I actually have to make an argument, like it's a trivial argument, but to say it's no, right, but I have to make that kind of argument anyway. Okay, so one note, one thing you notice about this reduction is that any non-optimal cycle has cost at least n plus alpha. It has to use at least one edge that's not in the original graph, or it has to use, right? So if alpha equals 1, then there's something that's interesting about this reduction. What if you have a nice condition for the traveling salesman problem, meaning that there's two kinds of traveling salesmen, okay? So there's some that are really fine, nice, reasonable people, and there's some that can never go back to the same town they've been to before, okay? And those people are not such pleasant characters, right? Maybe they're snake oil salesmen, right? So if you're somebody who can go back through a town you've been through before, or you can, then you obey this triangle inequality. And the triangle inequality says the distance from I to j should be no more than the distance from I to k and the distance from k to j. Because if you want to go from I to j, you can definitely go to k and then go to j. Right? That's normal, right? If you want to go from here to Sproul, I could definitely go to Bancroft and then go to Sproul for any place. I could go any place in between. That's called the triangle inequality. Okay? So it says that the one side of the triangle is no longer than the sum of the other two sides. Okay? So it says even this one is this hard. Even this sort of simple case is hard. On the other hand, if alpha is large, that it doesn't obey the triangle inequality, but either there's a cycle of length n or a cycle of n plus alpha. Now I can choose alpha to be arbitrarily large. I could choose it to be n squared, n cubed, anything for this reduction. And what that says is that telling the difference between n and 1 million times n, I can't even do that. It says I can't even approximate the solution. It's NP hard to even approximate the solution. If I approximate the solution within a factor of 2, then I would maybe, if I chose alpha bigger than 5n, then that would say, oh, there's actually a solution of 2n, which means there must be a solution of n, because there are no solutions of 2n. Okay? So having this gap between these two solutions says, for the case where you don't have the triangle inequality, you can't even approximate TSP within any factor. Okay? It's a really, really hard problem. Okay? Yeah. Yeah, any factor you want. I'll make a n log n here. Okay, what's your next one? No. What's your next factor? I mean, the point is, yeah, it's once you're allowed to do this kind of reduction and play with numbers this way and not have the triangle inequality, this problem becomes very difficult. Okay, so now I'm going to do, I want to do a reduction from every problem in NP to SAT. Okay, now I showed that all these problems are as hard as SAT. Now I'm going to tell you everything is as hard as SAT. I mean, no, what I showed you is all these other problems are as hard as SAT. And what I want to say, SAT is harder than everything. Okay? So that's the last step. Okay? So can people guess how this goes? Yeah. Right. So do people understand? What he said is you say SAT is a computer. Okay? And now if an NP okay, so this is in words, I'll do it in slides, but it's better for you to derive it yourself, so I'm just going to give you 10 seconds. Okay, no. Think about what SAT is. It's a computer, right? Think about what NP is. It says you have a program that can check an answer in polynomial time on a computer. Okay, so if you have a program that can check an answer in polynomial time on a computer, now a computer is a circuit. So that means you have a polynomial-sized circuit that can check your answer. Okay? Now a circuit, now what you need for this circuit to say yes or no is you need the right inputs for the circuit. You need the inputs that tell you the answer is yes. You need for a satisfying formula, you need the assignment. If you put in the assignment, then the program says yes. Anything else you put in, the program will say no. It can tell. Okay? So now you have a circuit that can tell you, if you could figure out how to set up the inputs, you would actually indeed have a satisfying assignment or a TSP2 or whatever the program is checking. Okay? So let me go through that a little bit more. Okay, so I think it's good to go without a net, and then we'll go with the net and see how it goes. Okay, SATs is hard, no. Okay, and so any search problem is reducible to SA3 SAT, and so that says everything is NP complete. Complete means what it means to be complete. It means any search problem is reducible to it. That's what it means. Okay. Okay, so let's look at circuit SAT. This is yet another problem. So this is a problem that, like he said, we used for linear programming, and I was even able to steal the figure for myself. And so the difference between circuits evaluation and circuit SAT, in circuit evaluation, these values were giving true and false. Here, circuit SAT is you want to figure out how to assign these values so that the output is true. You want to see what assignment of values you need to have here so that the output is true. Okay, that's what the circuit SAT problem is. It's very much like the SAT. You want to figure out what assignment of variables you need to have to make all the clauses true. Here you want to say what assignment of inputs do you need to have to make the output true for this circuit. Okay? Okay, so this is the problem. So now I claim that all problems in NP are reducible to circuit SAT. Okay, so and that's no, I'm not going to claim that. First, I'm going to say circuit SAT is the same as SAT. You can reduce circuit SAT to SAT, and we've seen this. So what we need to do is circuit SAT is a circuit. SAT is a set of clauses. So what I need to do is I need to write out a set of clauses so that those clauses are satisfiable if and only if the original circuit was satisfiable. Okay? So what I need to do is so what I'm going to do is just like the linear programming construction. For each gate, I'm going to introduce some set of clauses. Now, those clauses tell me that gate is operating correctly. That's what the clauses are saying. Okay? So for a true gate, I have a variable x sub g, and I have a clause x sub g. And x sub g better be true for this particular gate to be true. For a false gate, I add a clause not x sub g. Okay? And for that clause to be true, what does x sub g need to be? What does the value of x sub g need to be? Anybody? False. Okay? Okay, so you guys are sleepy and tired, and we're going to finish this on Thursday.